Assalamualaikum and a very good day to my panels and all the viewers. My name is Rima Nurkhairunnisa binti and I will be presenting my final year project titled Synthesis of Novel Organic Chelator for High Temperature Carbonate Stimulation Application under the supervision of Associate Prof. Dr. Muhammad Fazli Muhammad. First, I will start with what is chelating agents. Chelating agents are multidentate ligands that bind or coordinate with metal ions through their donor atoms to form high stability complex ring type structure. The metal ion consists of reactive sites which can enter into undesirable reactions in many cases. Hence, the use of chelating agents will prevent this metal ion activity by blocking its reactive sites. In oil and gas industry, matrix acidizing has been performed for stimulation of high temperature carbonate reservoirs. The main purpose of acidizing is to eliminate damage around the well bore caused by ion precipitation and thus increase the oil and gas production from the well. Besides, acidizing is used to improve the flow of hydrocarbons by generating wormholes through calcite dissolution in carbonate rocks via chelation of calcium ion. Therefore, to achieve this purpose, amino polycarboxylic acids such as EDTA, DTPA, and NTA, as well as hydroxyamino carboxylic acids like HEDTA and HEIDA have been utilized over the past few years. However, Pinto et al. 2014 emphasized that current commercial chelators such as EDTA, DTPA, HEDTA, and HEIDA have severe environmental impacts since they have strong ability to form metal complexes together with their poor susceptibility to biodegradation. Apart from that, a previous study by Fred and Folger 1997 revealed that EDTA can effectively create wormholes only when injected at either moderate or non-acidic pH levels, which is 4 to 13. Meanwhile, Frenier 2001 studied that the injection of HEDTA can generate more wormholes only at pH values less than 2.5 due to the presence of hydroxyethyl group in its structure that can enhance its solubility in acid solution, resulting in an increase of its binding capacity to calcium ions. Besides, according to Frenier et al. 2003 and Pinto et al. 2014, NTA is carcinogenic to humans and mammals, which has the potential to induce cancers. Hence, novel organic chelating agents are needed to be synthesized in order to overcome these problems. Amine diacetic acid appears to be a good alternative to substitute the conventional chelating agents for stimulation of oil and gas well. This is due to the fact that it is readily biodegradable and therefore environmentally friendly. Furthermore, amine diacetic acid is considered to have no toxic or carcinogenic effects. Last but not least, it is capable of dissolving calcite from carbonate rocks and removing the wellbore damage effectively during matrix acidizing over a wide pH range. The objectives of this study are first to synthesize amine diacetic acids by nucleophilic substitution of different primary amines. Second, to synthesize calcium complex containing amine diacetic acid via complexation. And third, to characterize the synthesized compounds using spectroscopic techniques such as Fourier transform infrared spectroscopy, proton NMR spectroscopy, and APT NMR spectroscopy. Moving on to the methodology. First, the synthesis of amine diacetic acids, which are N-ethylamino diacetic acid and N-propylamino diacetic acid. For the synthesis of N-ethylamino diacetic acid, a mixture of 2 mmol of ethylamine, 5 mmol of 2-chloroacetic acid, and 10 mmol of potassium hydroxide was refluxed in distilled water at 100 degrees Celsius for 4 hours. The mixture was allowed to cool at room temperature before removal of solvent using rotary evaporator. This procedure was repeated using different primary amine called propylamine to form N-propylamino diacetic acid. Subsequently, the previously obtained amine diacetic acids were used to form calcium complex containing amine diacetic acids. For the synthesis of calcium complex containing N-ethylamino diacetic acid, a stirred solution of 5.6 mmol of N-ethylamino diacetic acid in 20 ml distilled water was added with 11.6 mmol of sodium hydroxide. Then, 2.8 mmol of calcium chloride in 20 ml methanol was added into the mixture, and the mixture was stirred for 15 hours before the elimination of solvent by rotary evaporator. The steps were repeated to form calcium complex containing N-propylamino diacetic acid using N-propylamino diacetic acid as the starting material. Next is results and discussion. All the synthesized compounds which are N-ethylamino N-propylimino-diacetic acid and N-propylimino-diacetic acid, including calcium complex containing N-ethylamino-diacetic acid and calcium complex containing N-propylimino-diacetic acid, give off white color in the form of solid. To prove the formation of the synthesized compounds, spectroscopic techniques such as FTIR, proton NMR, and APT NMR were used. Here are my results for characterization of amine diacetic acids using FTIR. Based on both IR spectra of N-ethylamino-diacetic acid and N-propylimino-diacetic acid, all the peaks or bands observed are located at the similar wave number, as all the functional groups in both compounds are practically the same. The broad absorption bands at 3365.72 and 3375.09 indicate carboxylic acid OH stretch, and the bands at 1611.07 and 1723.08 indicate carbonate stretch. Next, since both compounds contain tertiary amine, no NH stretch was observed in the range 3500 and 3300. At 1391.11 and 1399.03, the peaks indicate carboxyl stretch. And lastly, at 1321.32 and 1228.04, the peaks indicate CN stretch. Next is proton NMR spectra. Proton NMR spectrum of N-ethylamino-diacetic acid differs slightly from N-propylimino-diacetic acid in terms of chemical shift and the presence of additional methylene peak in N-propylimino-diacetic acid, which is denoted as proton 4. As we can observe in both spectra, a tall singlet peak indicating proton 1 and 2 appears at the highest chemical shift of 3.171 and 3.938. This is due to the deshielding effect of electronegative nitrogen atom and carboxyl group. Apart from that, the singlet multiplicity showed that the protons are adjacent to a carbon without any proton. Also, in both spectra, proton 1 and 2 only produce one signal as they are equivalent by the plane of symmetry between them. For APT spectra of N-ethylamino-diacetic acid and N-propylimino-diacetic acid, they provide information about the signals of methyl carbon, methylene carbon, and quaternary carbon. There are 4 signals observed in both spectra. In APT spectrum of N-ethylamino-diacetic acid, the methyl carbon signal is positive, while the methylene carbon and quaternary carbon signals are negative. However, in the APT spectrum of N-propylimino-diacetic acid, all the signals are in opposite phase of N-ethylamino-diacetic acid. Proceeds with the characterization of calcium complex containing amine diacetic acids. Based on both IR spectra of calcium complex containing N-ethylamino-diacetic acid and calcium complex containing N-propylimino-diacetic acid, all the peaks observed confirm the functional groups present in the structure. As we can see, both IR spectra are similar to the IR spectra of amine diacetic acids. However, the changes in position of the characteristic peaks seen as compared to amine diacetic acids confirm the formation of complex. This is also implemented for both proton NMR and APT NMR of calcium complex containing N-ethylamino-diacetic acid and calcium complex containing N-propylimino-diacetic acid. This is the mechanism of nucleophilic substitution of ethylamine, where hydroxide ion attacks the two amine hydrogens, which are then displaced by two acetic acid groups. On the other hand, this is the mechanism of complexation of N-ethylamino-diacetic acid, where it undergoes deprotonation at the carboxyl hydrogens before coordinating with calcium ion. In conclusion, amine diacetic acids are a viable candidate to replace current commercial chelating agents such as EDTA, DTPA, NTA, HEDTA, and HEIDA used for stimulation of high-temperature carbonate reservoirs. In this study, nucleophilic substitution reaction between primary amine and 2-chloroacetic acid was applied to form the amine diacetic acids. Then, complexation of the amine diacetic acids with calcium chloride was conducted under mild basic condition to produce calcium complex containing amine diacetic acids. All of the synthesized compounds were confirmed by spectroscopic methods of FTIR, proton NMR, and APT NMR. Out of 2 synthesized amine diacetic acids, N-ethylamino-diacetic acid acquired a better yield than N-propylimino-diacetic acid, and the percentage yield of calcium complex containing N-ethylamino-diacetic acid was higher than that of calcium complex containing N-propylimino-diacetic acid. It is recommended to investigate on the synthesis of amine diester acids by using different primary amines other than ethylamine and propylamine, as the research on furnishing them has been one of the crucial development in oil field application. Next, further studies are required to assess the potential method of synthesizing amine diester acids with high percentage yield in a short refluxing period. This marks the end of my presentation, and I really appreciate your undivided attention. Thank you and have a nice day.